Hi, everybody. We are going to have a really quick discussion here about how the addition of functions has added another layer of complexity to our Python programs. So previously in our Python programs, we were all in the global scope, right? So you had your lines of code all aligned, like left aligned in your file. Everything could see each other. All your variables could see each other. Everything happened sort of top down, left to right. So any changes you made to a variable up here would automatically be still there if that same variable was accessed down here. But functions sort of alter this for us a little bit. So if you know other programming languages, you may have heard terms such as, let me just write them down. I'm going to put them in red because this is not what Python does. Not Python. Okay, but you may have heard terms such as Python is pass by value, or you may have heard Python is pass by reference. These are terms used in other programming languages, but they're not terms that we actually use in Python. Python does stuff in similar ways. We definitely have like an overlap in behavior, but that's not the terminology that we use. Similar to how other programming languages might call functions methods, we call them functions. So part of it is like a difference in terminology, and part of it is kind of a difference in how the Python programming language handles the like these control structures and these variables and this data, how it manages memory effectively. So in order to really understand this, what we actually have to focus in on is the term mutability, which is also used in other programming languages. Let me actually fix this up here. So what we're going to do instead is we're going to say that Python is pass by assignment. And we're going to define that in a second. But this is the one that's actually accurate. Okay, so let's, oops, that's supposed to be a check mark. So let's focus in on mutability for just a moment in time here. When we're talking about mutability, we're talking about two different types of objects. Everything in Python is what we call an object. We haven't really used that word very much yet, but we will see it again later in the course. Now, this idea of mutability effectively boils down to when I make changes, how does Python react? Okay, so it is a bit more nuanced than that, but that's what we're going to kind of work with. And we have two different types. There's like two different levels of mutability. We have object, and we have mutable objects. So those are our two different levels, and there's nothing in between. Things that are immutable include things like when we use ints, when we use float, like integers, floats, booleans, individual characters, or like a string, chars, slash strings. Those would all be immutable, and also tuples. Tuples are also immutable. Okay, so that's immutable. Then we can look at the mutable objects, and mutable objects are going to be things like lists, sets, dictionaries, and when we get there later in the course, we'll also be able to say custom objects, but we're not there yet. But it does fall into this category, so it is just worth mentioning. And so now the question is really like, why do we care about this, right? How does this concept of mutability affect, whoops, functions? That's what we're really going to try to answer here. So let's start with a function. Usually I like to write my functions in a different color when I can. Def function 1 x. X is equal to x plus 1, print x. And then back up here, we're going to say x is equal to 2, print x, function calling on, X and print X. Okay, so here's some code for us to look at. Here is like our global space, our global scope of our program. And here is going to be the local to the function scope. So we can see that we have these two different levels of scope, and we talked about scope previously as well. So this is not a video on scope. This is just going to be on this idea of immutable and mutable objects. So the very first thing that our code will do is it will read in this function. It will define this function. Python goes, okay, I know that this function exists. If we need it, I know it's there. Then our code comes down here and it makes the variable x equals 2. And then we have a print statement, which will go ahead and print out a 2. Then we have this function call. As we know, x gets put in and passes a parameter into the function. So 2 ends up right over here. We can do this like in red here. Red's not great, I guess. Right here, we're going to have a 2. We can see that this is going to be x is equal to x plus 1. If this x represents a 2, just like we talked about in scope, there is a locally scoped x. So this will be 2 plus 1 will become 3. And now x equals 3. And then we're going to have a print statement of print x equals 3. There we go. So we print 3. Now, you'll notice that there's no return statement on this method or this function, pardon me. And since there's no return of any kind, what happens in function stays in function. We're not bringing anything back with us. So when we come back out of our code and we, finished running this method and we come right here, our x remains unchanged by the changes that occurred in this locally scoped function. So this x right here goes looking for a value of x, and it will still just find x equals 2. And that's because we never returned the value that x was altered to be in here, right? We never actually did anything with that value. So this will be 3. Oh, pardon me. Wow. This will be 2. And this right here is representative of an immutable object, right? We said numbers were an immutable object, and we can see that that's the case here. How do I know that that's the case here? Because the changes that I made in this locally scoped area didn't actually affect the outer scoping of that variable. And this is because these are immutable objects. It means every single time you make a change to the object, right here is where we made a change to the object. Every single time we make a change, Python gives us a brand new object. We're going to break this down a little bit further before we look at mutable objects. It's not quite like this in Python, but let's just imagine for a second that we have all of the memory that Python uses to run our program right here, program memory. And what Python actually is going to do when we make a new variable, like at this level right here, is when we say x equals 2, it's kind of like saying x is going to equal some point in memory that we are going to set to equal to 2. So we can kind of think about this like an address, like our house address, like 123 Fake Street. And when we go asking x, hey x, where can we find your data? X says, go look at 123 Fake Street, and that's a memory address. And when we go look at 123 Fake Street, we see right here that there's a 2 in there. So it's not that x is like a box containing a 2, right? This is not what we have. It's not like you're carrying the 2 around in your pocket. If you were value x, you're not carrying a 2 around in your pocket. Rather, if you were x, you're carrying around a piece of paper in your pocket with the address of where to find the value 2. It's sort of the difference between carrying a physical book around with you and carrying like the catalog number of the book in the library. So one is like you're carrying the call number, and one is you're carrying the physical book around with you. When we carry our cell phone in our pocket, we're not carrying the entire internet with us. We're just carrying around all the URLs that we could possibly need to find that information. It's the same idea. Maybe that'll be an analogy that sticks with people, right? If we carried the entire internet with us, it'd be really big and heavy and bulky, and you couldn't do it. So instead, we just carry around all the addresses we need. This is the exact same idea. This is exactly what Python does. So when Python passes in the value 2 here, it happily passes in the value 2 But really what it's doing is it's passing in this memory address. It's saying, here, you can find the value 2 at 123 Fake Street. So inside the method comes here and we get x plus 1. So it says, go to 123 Fake Street and get the value there. So we do, and we get 2, and add 1 to it. And so then those become 3. Now, every single time we have equals on an immutable object, Python says, oh, hey, that is a new object. You want a brand new memory address for that object. So Python will effectively at this point, I'm going to use purple because this line here is purple, will effectively make a second X object with a brand new address, 456 Fake Street, and give it the value of 3, 456 Fake Street. Now, what's important to notice here is that this still exists in its original state, and this now exists locally scoped to this, because that's where that purple is. So 2 came in right here, right from here. That is still the same. We can even turn these black. It might help, because those came in as those values from this black object right here. But as soon as we said assign, as soon as we said that this x equals that other value, Python said, no problem, enter immutable. So I'm going to give you a brand new piece of paper with a brand new address to your new value. It didn't actually overwrite the old value at all. So now print happened, and print on x at this point, remember how scoping would work here, right? It's going to go ahead and print that x right there, because that is our x value that we've actually recently updated. Perfect. So it's really not that simple. It doesn't really come down to like this equal sign or anything like that, but I'm hoping that this will kind of help bring our understanding along in something that's actually a very, very complicated subject and an abstract subject to understand. So then once our method ends, once we have finished this final print statement right here, and we kind of leave this method and we say, okay, bye method, and we like come back over here, we can't access anything that was purple out here. So what does that mean? That means Python comes along and says, oh, you can't see this anymore. You can't get to it because you left the method. You didn't bring it with you. I'll just delete it. I'll just get rid of it for you. So then when we do this print down here, Python only knows about the X that was black here, right? That was this one, right? It only knows about that one. So when we do this print, it's still that unaltered 2. This is our immutable object. And this is true for all of the data types that I labeled up here. Ints, floats, booleans, chars, strings, and tuples. All of those are going to act just like this example because they are all immutable. Okay, now let's look at a different example here. Let's look at mutable types. And let's give ourselves another example of the code. Here is going to be a second function, function 2, and this time it's going to take in a list because that's one of our mutable objects. Ooh, something weird just happened there. I want to make sure I'm like still screen recording. Yes, I am. Okay, mutable objects lists right there. So this is going to be a mutable object. How do I know if I'm still screen recording? Okay, I am. How do I know if I'm still, this will be very silly if I am still recording. Oh, I am. Good. Okay, I just want to make sure I don't want to lose this video halfway through. Okay, so let's do the mutable object option here now. So let's say we pass in a list and we add a value to that list the way that we've previously done. List dot append. Let's just add the value 4 to our list. It doesn't really matter. This is happening inside a local scope. This is at this outer scope, just like we had before. But then also at the outer scope, we have to call this function. So let's make a list. I don't know, 1, 2, 3. Let's go ahead and print it. There we go. Let's call our function 2 with our list. And let's print it. Oh, I added an I in over here, which I shouldn't have done. Sorry about that. Okay. So let's finish this example. Then we're going to talk a little bit more about the difference between immutable and mutable data objects. It will all kind of come together here. So this is going to be an example in mutable objects. All right. And let's draw it with that same idea of like the space that Python runs our code in. Here's our memory that Python uses. So again, we have a list variable here. And because everything in Python is kind of stored as if it's like URLs in your phone, at 1, 2, 3 Fake Street. We'll just keep doing that. It doesn't really matter. And then over here in memory somewhere, 1, 2, 3 Fake Street is your actual list. Now, typically we end up drawing lists or arrays kind of like this. 1, 2, and 3. There we go. Okay, so now, you're walking around. When we say print list right here, the print function inside Python like sees, oh, 1, 2, 3 Fake Street. Let's go into memory, find the data you've stored at that memory position, and let's print it out. So what are we going to get? Well, this will literally print out our list, which is fantastic. Now, again, just like previously, we're going to pass at 1, 2, 3 Fake Street into function 2, which means right here, we have another list variable here, list. I'm going to make it purple for a second. That also, whoops, it's purple, so it's differently scoped, but also references 1, 2, 3 Fake Street, just like the previous. Okay, so this example is exactly the same as the other one. I'm just going to now take it one step further with sort of giving memory addresses to those purple local variables. Okay, so now when we say list.append for, what we're actually doing is saying, go to that memory address and append a 4 to the list. So we end up appending a 4 to the list at that memory address right here. Now, again, I told you I was kind of oversimplifying, but I do want you to notice that here we had an equals, and here we don't. Here it's a dot append. It's a dot notation function call on our list variable. So now our function ends, and when our function ends, we can't see that purple list variable anymore, which means Python is like, oh, no problem. I'll just get rid of it for you because you can't reach it anyway. But you'll notice that what it did was it cleaned up the variable, but it didn't touch the change that we made to our list. That's attached over here, and we can still access 1, 2, 3 Fake Street. Before, in the example we had up here, we had 4, 5, 6 Fake Street, and we had a memory address, 4, 5, 6 Fake Street. When the variable disappeared from 4, 5, 6 Fake Street, we had no way to get back to that memory address. So Python just got rid of all of it for us. But here, that's not the case. Here, 1, 2, 3 Fake Street and 1, 2, 3 Fake Street are the same. This change it will persist because the purple list variable we can't reach, Python cleaned it up, but the purple change in the attachment of this, no problem. We can actually still reach that with the black variable coming from our global function, or pardon me, our global scope, because that was all the way up here. So what that means is after we've now finished this function call right here that we just finished, we go down here to print, and we call print list again, just as we did before. The difference being now, this is what our list looks like. So we're actually going to print out now 1, 2, 3, 4. There we go. And so now we can see that the change, even without a return, there's no return here of that list. Even without a return value, we are going to have the value persist in that memory address. In order to have that happen here, we had to have that persist situation. So let's talk about that now. I'm going to go ahead and just copy paste this example for just a moment down here with a return, just so that we can fully appreciate what it is that's happening here. Oh, wrong color, sorry. X, 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 X. We can understand this a little bit more, I hope, now that we've seen mutability. So I'm going to change all of these to be locally scoped in here. This is the locally scoped stuff. And then this is going to be the globally scoped stuff. And I can even move this over just to make it a bit more obvious. And we'll draw this out again. Okay. So now we're going to take this one step further just to fully illustrate this. Let's pull this down. Let's extend this a little. We can say return. Oh, that doesn't spell return. Return x. There we go. And then we can change function here to now say x equals return. Okay, let's walk through this step by step to understand what's happening here. So the very first line of code that actually executes for us is like, okay, yeah, we define the function, but then we have this x equals 2. So a reminder that that's like x, like storing a memory address in your cell phone. For ease, I'm just going to put at 123. We don't need at fake street each time. It would not be a real address like that anyway. So at 123, there's like a piece of data here that says 2. Okay, then we go to print whatever's at 123. So as we've already seen, this means we print out the value 2. Then we go into our function. We're going to execute this side over here first, and then we'll come and do this side. So we pass in the URL, the address, and it's going to be right here, 123. This says x is equal to x plus 1. So when we entered this function, we got a brand new variable that looked like this. They're both pointing to the same address, but we do have now an internal purple variable that is identical to the black variable from our external global scope, but it does exist in here. So now when we say x is equal to x plus 1, we are going to do this value first. We find that the purple x's address does indeed lead us to a 2. We're going to add 1 to it. We're going to get 3, and we're going to stick it in x. But because ints are immutable, this is going to change this address to a different address. There we go, 3. And now when we say print, we're going to print whatever's at 4, 5, 6. So we print out 3. Fantastic. Then we return x. So what this means is we're going to return the memory address that x is representing. Because as soon as we leave this function, this variable will once again disappear. But this time, we're going to take the memory address and we're actually going to store it back in x. So return x means this address right here is going to change from at 123 to at 4, 5, 6. When that function ends, Python will clean this up for us. And now look at this. We no longer have anything that's pointing to the reference at 123 because this reference is now pointing at 4, 5, 6. So Python will probably clean this up for us too. I don't know very much about Python's garbage collection, but point being, we no longer have access to that memory address because what the bookmark that we kind of were holding that memory address in, that X bookmark right here, has now been reassigned to a new value, right? It's been reassigned to 4, 5, 6. So now when I go and print X, this will print whatever is at 4, 5, 6, which as we just saw and returned is 3. So why is this the case? How does Python decide, I guess, what is going to be mutable and what isn't going to be mutable? Let's figure that out now. What criteria makes something mutable versus immutable? And at a very broad sort of analogy level, we're going to say it's because Python wants to work smarter, not harder. It wants to be lazy. It wants to be as lazy as it possibly can be whenever it can be. So when you think about the data types that are considered immutable, when we think about strings that we've created, or so like hello, just an example, integers, floats, Booleans, or even a tuple with two pieces of data in it. Every single one of these has a deterministic size, right? Deterministic size in memory. Once you've decided what your string is going to be equal to, we can figure out the size of a character times the number of characters, and that's how much memory space we need. We know that an integer needs like 8 bits or whatever. I don't actually know. It's embarrassing, but it's something like that. We know that a float needs however many bits a float needs. 32? I don't know. Unsigned bits? Those are words that get too low level for me right now. We know that a Boolean is either a 0 or a 1, right? It's either true or false. So this is basically stored in the same way that an integer is stored. And we know that a tuple needs to be able to store 2 memory addresses. It's important that I'm saying it like that because we don't know what these are, right? These could be strings, these could be ints, these could be floats, these could be Booleans, these could be lists for all we know. But what we can see is that these are all predefined. So Python can very lazily understand how much space it needs to allocate in memory for these data types. When we look instead at the mutable data types, such as a dictionary, right? A list, a set, quite unique, and any other objects that we might make, which we'll learn more about later. More on this later. What do we notice about these? These are things that can dynamically change size, right? These are dynamic sizing in memory. Dictionaries, lists, sets, let's just focus on those 3 for right now, since those are the 3 that we know. We can add to these lists and dictionaries and sets. We can delete from them. We can update values in them. They can grow and shrink. And so carrying something around that might grow to be 10 million elements, it just isn't good practice, right? Like you get really tired if you had to carry around 10 million of anything as a human. So Python, trying to be smart, says, well, okay, if there are some things that I cannot carry around because it just may not become feasible, I just won't. So I'm going to keep these in a separate pool of mutable things. And then that way, since I can't carry them around directly, if somebody makes a change to one, it will change it everywhere because it's kind of just shared everywhere. It's not easy to make a copy of it. It's not easy to know if it's going to dynamically grow and shrink, right? It's not quite as deterministic in its size. Okay, so we can see there's 2 different things that we have to consider here. So something to consider when you're doing anything around passing things into functions and the mutability of the objects is to draw it out, is to really think about this table here, because something that is a tuple, but perhaps it's storing 2 lists, this needs to be returned for the changes to be propagated. Changing list values alone wouldn't be enough. You'd have to actually return the tuple out of a method in order to see those changes propagate. So in my next set of videos, I'm going to do a few different examples of questions where we can sort of see this and break down its usage and how it works. Yeah, okay, thanks everyone for joining me for this video, and I'll see you in my practice problem video set.